In this topic, we are going to talk about how we can re-express a given expression into its partial fraction. But we are not talking about any expressions. We are talking specifically about expressions that are of the rational expression format, which means that we require the numerator and the denominator to be both polynomials. And polynomial is one of the topics that is in our syllabus. So in order for us to learn partial fraction well, we need to first make sure that we are well versed enough with polynomials. So assuming that you guys have already been learning polynomials well, let's then proceed with partial fraction. I'm going to make use of this example, and we are trying to re-express this into its partial fractions. And to do that, I'm also going to be making use of the few steps that I've highlighted in the outline. And the first thing that we need to do is we want to make sure that we are working on only proper fraction. But if you were to look at this example, this is not a proper fraction, this is an improper fraction. We have learned in the topic on polynomials that as long as the degree of the numerator is more than or equal to the degree of the denominator, then it is improper. So the degree of the numerator here is 3 and the degree of the denominator here is 2. So we are looking at an improper fraction, and the first step that we are looking at is we need to obtain proper fraction. So what we want to do now is let's carry out a long division to re-express this. So I'm going to take the numerator, which is x to the power of 3 minus x minus 1, but it's lacking a term x to the power of 2. So if we were to do a long division, to just make sure that the whole process is a little bit more simple so that it is more typical, we're going to add in a x to the power of 2. And this is what I'm going to do, x to the power of 3. This is from the numerator. And for x to the power of 2, I'm going to write it as plus 0, x to the power of 2 minus x minus 1. And I'm going to do a long division of this. So this is the dividend. I'm going to divide it by the divisor. The divisor is x to the power of 2 plus 3x plus 2. So we're going to take this divided by this. And I'm going to try to remove x to the power of 3. So here I'm going to go for x. So x multiplied by this gives me x to the power of 3 plus 3x squared plus 2x. So I'll take this here minus this. So this minus this, we have a minus 3x squared. This minus 3x. And this, I'm going to bring it down, so it will be minus 1. And we're going to try to remove this. So I'm going to multiply the divisor by minus 3. So minus 3 multiplied by this will give me a minus 3x squared minus 9x, then minus 6. And let's minus this expression from this expression again. So this minus this is 0, this minus 9, so it'll be minus 3 plus 9x. This will give me a 6x, then minus plus 6, it will be plus 5. So this can now be re-expressed. It is going to be equal to x minus 3 plus 6x plus 5 divided by x squared plus 3x plus 2. Okay, and what we are going to do is we're going to focus on just this portion, the portion where the proper fraction lies. Okay, so this is already okay, so we are not going to touch it. We are going to focus on this, and let me just rewrite this here, okay? So we are going to look at how we can re-express the proper fraction portion into its partial fraction. So this is x squared plus 3x plus 2. Let's move on to the second step. The second step is to make sure that we factorize the denominator as much as possible for the proper fraction portion. So this is the proper fraction portion. For the denominator, let's try to factorize it. So we have 6x plus 5 divided by, for the denominator, we have x plus 1 and x plus 2. Okay, so now we have already factorized the denominator. The next one is to follow this set of rules to re-express the expression, the fraction that we currently have, into its partial fractions. So for this set of rules, let me tell you how we can make use of it, okay? We need to look at the denominator, the terms that are in the denominator. So for example, if in the denominator it consists of ax plus b, then its partial fraction is going to look something that is like this. In fact, this is the example that we are doing. So in this example here, the denominator consists of linear expression ax plus b. So we're going to follow this rule. For the denominator, which is a linear expression, it is going to become a partial fraction where it is going to be a constant divided by this linear expression. There are two other forms that are in our syllabus. We are going to talk about them shortly. So let's just make use of the first row in this table first. Okay, so I'm going to re-express this. So we are going to try let this, the proper fraction portion, where the denominator has already been fully factorized. So we have a x plus 1 and a x plus 2. I'm going to rewrite this as constant over the linear expression plus constant over another linear expression that is given, so x plus 2. If I were to have the third or the fourth linear expression, it will be plus c over the third linear expression plus d over the fourth linear expression, okay? And it will just continue. So it is going to be this, and after we have done this, we are going to try to step 4, multiply the left and right hand side. In fact, it is just multiplying throughout this equation by the LCM of the denominator. Okay, so for the LCM of the denominator, it is x plus 1 times x plus 2. So I'm going to multiply this entire expression throughout by x plus 1, x plus 2. So on the right hand side here, we are going to be multiplying this by x plus 1, x plus 2, and the same goes for the left hand side here. We are going to multiply this by x plus 1 times x plus 2. So for the left hand side, I think it is pretty straightforward because this and the denominator will be immediately cancelled. So we are going to be having a 6x plus 5. This is going to be equal to, so this multiplied by this, x plus 1 and x plus 1 can be cancelled. We're going to be left with a times of x plus 2, then plus b of this, and this can be cancelled, b of x plus 1. So after we have done this, we are going to then apply the last step, which is to apply polynomial identity to solve for the unknowns a and b. Polynomial identities was what we have touched on in the topic on polynomials. So we have two strategies, two methods for us to be solving for unknowns. One is to make use of substituting numbers, substituting convenient numbers. And the second method that we have talked about in the topic on polynomial is to try to compare coefficient. Looking at the case that we have here, I think substituting numbers will be good because they are indeed pretty convenient numbers for us to be substituting into this identity to solve for a and b, because I can immediately solve for a by letting x to be equal to minus 1. Because if I were to let x be equal to minus 1, this is where I found my inspiration, okay? Because if I were to let x be equal to minus 1, on the left hand side it is going to be 6 times of minus 1 plus 5, and on the right hand side it's going to be a times of minus 1 plus 2, and this is going to just disappear. It is going to be equal to 0. This will give me the value of a, and a is going to be equal to minus 1. And I'm going to substitute another convenient value of x, which is actually minus 2, because that will immediately cause this term here to become 0. So when x is equal to minus 2, on the left hand side we have a 6 times minus 2 plus 5, and on the right hand side this will become 0 plus b of minus 2 plus 1. This will give me the value for b. b here is equal to 7. So now, since this is equal to this form, therefore we can then express 6x plus 5 over x plus 1 times x plus 2 in the form of a, which we have found it to be minus 1. So minus 1 over x plus 1 plus b, which is 7. So plus 7 over x plus 2. But of course, we should still try to answer the question. So if I were to just replace this, which is now in its partial fraction form, then re-expressing this into its partial fraction will get us an expression that is like this. X minus 3, which is still going to remain. So we're not going to touch this particular expression here, x minus 3. So x minus 3 plus this, which is now this. So the first term is minus 1 over x plus 1. Then the next term is plus 7 over x plus 2. So this is it. Okay, this is partial fraction. This is how we can re-express a given expression into its partial fraction. Let me just show you two more examples because it is a very simple topic. I believe with these two other examples, you guys should be able to do most of the questions that will require you to carry out a process of re-expressing something into its partial fraction. The second example that I want to show you is actually going through the same process, but we are going to be trying to re-express this. Okay, then the last example will be this. Let's take a look at this second example over here. Okay, now we have another expression, and this other expression is x plus 1 over x plus 3 square and x minus 2. So x plus 1 over x plus 3 square, x minus 2 is a proper expression, which means that if I were to still follow this process, in fact, we should be following these few steps here, okay? We can skip step 1. Because we are already being given the proper expression, the proper fraction. So we don't have to carry out any long division. The degree of the numerator is equal to 1 and the degree of the denominator is equal to 3. It is a proper expression. So since we have already gotten a proper expression, let's move on to step 2. Step 2 requires us to factorize the denominator of the expression, the proper fraction that we have, and this is the maximum we can already factorize the denominator, so I don't even have to do part 2 also. Let's just go directly to part 3, which is obviously this that we are going to be working on since I'm using this particular example. But if let's say this is a fresh question, okay, if I were to look at this and we're supposed to re-express this into its partial fraction, so the first thing that I'm going to do, since we are skipping step 1 and 2, the first thing I'm going to do is I'm going to just try to rewrite this into its format according to the table that is given. So x plus 1 over x plus 3 square, x minus 2. So we have a x plus 3 square. If I were to look up the table, yeah, this is the part where it looks like a x plus 3 square. Ax plus b, the whole thing square. So when we see signs of this kind of expression in the denominator, then this is what we will do. Okay, we will rewrite this as a over x plus 3. This is x plus 3 square. So we just write it as x plus 3, then b over x plus 3 square. Okay, which means that the moment when you see this, you actually evolve into two terms. And then we have a linear. If it is a linear term, we're going to go back to make use of what we have in our first row, where the denominator is a linear expression. So this is going to be plus c over x minus 2. And we are still going to try to solve for the unknown coefficients, the unknowns a, b, and c here. And to do that, step 4, we are going to try to multiply this entire equation by the LCM of the denominator, which is x plus 3 square multiplied by x minus 2. So on the left hand side, if I were to multiply by this, we are going to be just getting a x plus 1. And on the right hand side, if I were to multiply by this, so this multiplied by this, we're going to have a of x plus 3, x minus 2. And this multiplied by this expression in the denominator, it is going to be plus b of x minus 2. And for this, if I were to multiply by the denominator, so this expression will become c of x plus 3 square. And we are going to try to solve this polynomial identity. And I'm going to try to substitute convenient values of x first. And one convenient value of x that I can substitute in is 2, because 2 is going to cause this to be 0. When x is equal to 2, it's also going to cause the second term to be equal to 0. How convenient that is, right? So we are going to go for x to be equal to 2. So on the left hand side here, it is going to be 2 plus 1. This will be conveniently 0. And this is also going to be 0. Plus c times of 2 plus 3 square. This will help us to solve for c. Let me see, what is c going to be? C is going to be equal to 3 over 25. And is there any other convenient values that we can go for? I guess x is equal to minus 3 is convenient, because when x is equal to minus 3, this is going to become 0. This will also become 0. Then we can solve for b. So let's go for this number 3. So when x is equal to minus 3, let's go for this number minus 3. So we're going to go for minus 3. On the left hand side, it is going to be minus 3 plus 1. This is going to be 0. And plus b times of minus 3 minus 2 plus this is also going to become 0. And we're going to get the value for b. And b is going to be equal to, let's see, b, if you were to evaluate this, b is going to be equal to 2 over 5. And now we have the value for b, we have the value for c. As for a, I don't think there are any values that are so convenient as what we have done in these two parts. But I guess we can just throw in a 0. Okay, I think 0 is easy for us to evaluate also. So I'm going to go for 0. I just need to go for a value that I've not used before. So we have used 2, we have used minus 3. Let's go for 0. So on the left hand side, it's going to be just 1. It's going to be a times of 0 plus 3 is 3, 0 minus 2 is minus 2, plus b is 2 over 5 of minus 2, plus c is 3 over 25 of 3 squared. This will help me to solve for a, and a here is equal to minus 3 over 25. And we have found the values for a, b, c, which means that the partial fraction of this, let me just write it down here. So therefore, we can now say that x plus 1 over x plus 3 square, x minus 2 is going to be equal to a, which is minus 3 over 25. So minus 3 over 25 of x plus 3 plus b is 2 over 5. So plus 2 over 5 of x plus 3 square, and c is 3 over 25 of x minus 2. Let's look at one more example. I'm going to make use of this particular example here. So we're going to be working on now an expression that is this 3x squared minus 4 over x squared plus 1 multiplied by x. We are supposed to re-express this into its partial fraction. We are going to be skipping step 1 because we are already given a proper fraction, so we don't need to do any manipulation to the expression given. Step 2, we need to factorize the denominator, and if you can take a look at this denominator, x squared plus 1 times x, it is already fully factorized. Some students have this little bit of confusion between an expression that is x squared plus 1 and an expression that looks like this, x squared minus 1, because x squared minus 1 can still be factorized. X squared minus 1 can be seen as x squared minus 1 squared, which means that this will become x minus 1, x plus 1. But x squared plus 1 cannot be factorized any further. So this is the max we can go for the denominator. We have to move on to the next step, which is to re-express this into its partial fractions format. And we're going to take a look at the denominator that we have. So this is going to match to this over here, x squared plus c, where c is a positive number. So we have c as 1 in the denominator here, okay? So x squared plus a positive number. So when we see this, the format will be like this, which means that for this x squared plus 1, it is going to be like ax plus b over x squared plus 1. And the other term is a linear term, so it's going to follow this ax plus b, which will be a constant over ax plus b. So the constant that I'm going to go for, I'm going to make use of the alphabet c, so c over x. And we are going to move on to the next step. I'm going to multiply this throughout by the lowest common multiple of the denominator, which is going to be this entire expression in the denominator, x squared plus 1 plus x. So if I were to let this expression here be this format, that means multiplying throughout by the denominator, the LCM of the denominator. On the left hand side, we're going to be getting just this. And on the right hand side, this entire expression multiplied by this will give me an ax plus b multiplied by x. And this multiplied by this entire expression here will be c of x squared plus 1. And I'm going to try to, again, substitute convenient values to solve for this polynomial, this identity polynomial. So I do see a very convenient value, which is 0, because it's going to cause this entire expression to be 0. So when x is equal to 0, on the left-hand side, we have a minus 4, and this will become 0. And we will have a 0 squared plus 1, which is 1. This tells me that c is immediately minus 4. I guess there's not really that many more convenient values that I can use for this particular identity. So I'm going to just sub nice values. For example, I'm going to go for 1. I'm going to go for minus 1. When I go for 1, so when x is equal to 1, on the left-hand side, it is going to be 3 times 1, which is 3 minus 4, is going to be equal to a times 1, which is a plus b times 1, then plus c, which is minus 4, 1 squared plus 1, so it's going to be 1 plus 1. This gives me an a plus b is equal to 7. Okay, I cannot really solve for a or b in this case. Let's go for another value first, okay? I'm going to show you why this is still possible for us to be solving for all the unknowns a, b, c. So when x is equal to minus 1, on the left-hand side, 3 times minus 1 squared is still going to be equal to 3. So it's going to be 3 minus 4 is going to be equal to a times minus 1 minus a plus b times of minus 1 plus c, again c was minus 4, we found that previously, and minus 1 squared is going to be 1. So we have this. So now we have a minus b is going to be equal to 7. Okay, so although we couldn't solve a or b here, neither could we do that. I mean, neither can we do that here, but we can now have a pair of equations that involve a and b. So what I'm going to do is I'm going to try to solve this as a pair of simultaneous equation. So we have this and this. Oh, nice, because b minus b, I'm going to just take equation number 1 plus equation number 2, which will help me to immediately remove b. So it will be this plus this, which will give me a 2a on the left-hand side, and on the right-hand side is going to be 7 plus 7, so it's going to be 14. This tells me that a is equal to 7. I'm going to substitute this back into either equation number 1 or 2. Let's just go for 1. So if I were to substitute a is equal to 7 into equation number 1, then what we will have is going to be a 7 plus b is equal to 7. This tells us that in fact b is just going to be 0. Therefore, now we can also successfully re-express our last example here into its partial fraction. So 3x squared minus 4 divided by x squared plus 1 times x in its partial fractions is going to look like this. A, which is going to be 7. So 7x plus b, which is 0, so plus 0. We are not going to write that. Divided by x squared plus 1. Then plus c, c is minus 4. So it will be minus 4 over x. And that's it, guys, for partial fraction. It is a very easy topic, and we're going to be getting marks for this because I think in exams, this topic is going to be pretty generous when it comes to question. Okay, so if you are okay with this, let's move on to the next chapter, and I'm going to see you there.